All right. Hi, how are you guys doing today? Welcome to the October Perl Mongers meeting. The topic is how to listen to your children, or really just a fancy way of saying concurrence. First thing that I learned is that concurrence, wrong button, concurrence is not parallelism. And to me, I didn't think that it was a problem, but I guess a lot of people need this explained to them. But concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once. This is from a Golang blog that we have linked in the references. It's actually from a talk by Rob Pike, and the demonstration, the image is stolen from someone else. But basically, the idea of concurrency is you would think if you only had one processor, but you wanted to do a whole bunch of things, the processor would switch back and forth and back and forth. You're really not doing parallelism. Parallelism means literally you're doing something at the exact same time. Doesn't really happen. You know, it's like being able to, what is that, pat your head and rub your belly thing? I can't do it. Some people can. But the idea of concurrency, I guess parallelism is concurrent or concurrency. But not everything that's concurrent can be parallelized. Parallelism, as it's shown here, these are things happening side by side. But concurrent ideas, they can happen side by side too. But sometimes you can have concurrent issues that require information from one step to the next. If you have parallel ideas that require information from each other, that's a bad time because that's called a race condition. And just one of them is going to blow up in your face. So just to kind of give just to lay the groundwork, concurrency is a logical block, or you want to think about concurrency in logical blocks. What can I do at one time? And then once you figured out this block, then you can think of, can I do this a lot, all at the same time? Or do I need to make this one start and wait for the other one to finish, and then I can do a lot more? But maybe you can have several blocks that can happen in parallel, but then require to fire off more blocks. This isn't going to be that cool of an example, but you'll get the idea. Basically, concurrency, unlike parallelism, concurrent blocks can have independent start and stop times. You can run them in parallel, but there's the difference. Slight difference, and I guess on the internet people have arguments about it, so I just thought I'd throw that in there. So the problem that we're talking about today is stemmed from a health check problem that I had. Basically, we have a system that has a health check, and of course I thought I'd sorry, this was already before I restarted the...
Is something you can make publish?
well, actually, yeah, there is not obviously this, because this is all running on my laptop, but if you do go to the GitLab, which I linked on the front of this...
No, I meant you're not about to show something.
Oh, no. Yes. I'm sorry. This is, yes, this is allowed to be viewed public. In fact, everything you're about to see is a contrived example. Through the power of Docker, I have 101 servers serving up health checks, all of which are dummies, with the exception of, where is it? Database. Oh, there we go. With the exception of this touch file. So I can kind of go into this. We're going to go into it anyway. So I wrote a health check. Sorry. Somehow everything rearranged itself on my desktop because this was supposed to be here. Okay. So I wrote just a simple health check script, which is now hiding from me. Is that a good size? Okay. So basically, all it really does is you hit the it runs a PSGI server. The app, all that it does is it serves back this body. And the only thing it does is it looks to see if a file exists and then says success or failure. And that's that way we can get a little bit of variation. I've basically set a script up that started 100 of these instances, and about 20% of them are set to fail. The other 80 will be good. So, and we'll see this. And to make it even more interesting, because this isn't very interesting or shows any real-life examples, I set it to sleep for up to 10 seconds randomly. So we have a server that has a health check, so that's good because we have something that's made some progressive steps. But we want to be able to monitor the health. It's not just we have the one server, we have 100 instances. And it's not like, well, we can write a script that can check them real quick because the idiot who wrote them didn't write them very well because, it takes up to 10 seconds to come back. So, that's the problem. So, the first real thing of tackling this is, well, we have to be able to have a visual representation of what's going on. So we need a dashboard. And, honestly, if just for visual representation and understanding what's happening in your system, the dashboard works really well. Obviously, if things go critically wrong, you want some active alerting going on that's going to tell you that, hey, your whole thing is going down. But the question is here, is this a bad state for the system? If this is 101 instances all serving the same function, is it okay that we have, 15 of them down? Should I be woken up in the middle of the night by this? Probably not, because in the middle of the night, who's really using my service? It's not a popular service. But so you have to have alerting. But you come in the morning and you want to know what your health of your system is as a whole. If you just have alerting, all you know is that, well, at least 80% of my things are up. But if you've come in the morning and you have 15 down nodes, wouldn't you want to just make those things whole? Not that you go home and then all of a sudden the 21st fails and then you get the PagerDuty. So that's where like a dashboard like this can be a simple solution. And there are many ways of displaying the information. But the core problem is that something still needs to go out and talk to every one of these nodes and look at their health check. And, as a nice thing for this health check, I basically made each one a link. And, of course, it takes up to 10 seconds to render. And like this one, yeah, it's successful. Here's why, why it's successful. If we want to find out why did this one fail, we go to it. We also have to, I should have probably had a shortcut where I could say don't fail, don't wait, and it'd come up real quick. But anyway, the person who wrote this was an idiot and wrote it really long. Of course, that one does say success. But it says, I need to refresh the dashboard? Okay, I bet you this one's actually failing. So anyway, as you can see, having one person check all these machines. All right, there we have a failure. Failed. It's failed because, check if file exists. Existent means that the server's in rotation. The touch file, it's a failure. It does not exist. I can go on, figure out is it actually down? Did someone delete the file? And so forth. So anyway, dashboard, very nice tool, very handy tool to have. But now comes the question, how do we get all this information? So the first approach is blank. There we go. The first approach is we write a script. And as so happens, I've written a script. And I called it health check first. Very simple script. Basically, it gets all our nodes. I created a config file that has the number of nodes that we're doing, so I can change these things quickly. But basically, it just goes through all the available nodes. Obviously, in a production system, you would have something else that says, give me all my servers. But that's what all this is doing. It hits it gets the health check. It just needs to do a LWP simple. I can show you that if you're interested. But it just gets it. It strips out the status and the host name, puts it into this object, and then it basically writes the file from this. The other scripts I'll actually run and show you. This one I won't. It takes 8 minutes. I ran it enough times to get some data points, and it was just sad while I had to wait for it to finish running. So needless to say, just writing a script, if you have 5 servers, that's great. It'll work. It'll take 50 seconds. You can run that every minute, and you'll have a kind of real-time understanding of what's going on in your system. But when you have more than 6 servers, that becomes a problem. So what do we need to do? Well, basically, I'm having something. Oh, okay. Something really weird happened with my presentation. I apologize. So the problem with writing a script is that with 10 seconds of a pop, it just takes a really long time. You cannot, this doesn't work. You can't wait 8 minutes to, unless you don't mind waiting 8 minutes and being 8 minutes behind on what is supposed to be the snapshot of your system as a whole. So we turn to fork to the rescue. Basically, what does fork give us? It creates a new process running the same program at the same time. Yay, we have parallelism, kind of. Caveats as the whole program is duplicated. So you don't want to do this with a monolith. If you do this with a monolith, you do it more than once, you're probably crashing your server. Not good. Probably run out of memory. So whatever is actually monitoring your systems needs to be a smaller program. Obviously, now that you're using fork, you are using something a little bit more platform dependent, although this presentation easily works on Linux and Mac. If you're on Windows, Perl tries to work in that environment, and there is a fork for it as well. But realize once you start forking things, you're getting a little bit more system specific. And of course, responsibility. You are spawning children. You are not allowed to neglect your children. I hear that's good advice for other things too. So why not use threads? Well, frankly, I skipped ahead because we're going to go back to the threaded one, but to the forked one in a second. Frankly, I don't know that much about threads. And I've been told that they are not ready for production. Actually, I was very wrong on that because I started reading up on threads earlier this week. And if you guys are interested, I can do the next talk about threads because they are now safe using the modern iThreads. Anybody interested in threads for next time?
Perl 5.
Yeah, Perl 5. 5, 10 and above using iThreads. If you're 8 or below, that is the unstable threads. Don't use it there. But anything with the modern ones, yeah, they are stable. And it's actually some really cool stuff. So, example, back to the fork, and it again, now we will be using parallelism because what is a good thing in this mess? What can we, write to parallelize? The one thing that we can kick off over and over again, get health check. Getting the information, that's all that we need, is that we can do that 1,000 times, we can do it once, but we can, getting health check from the first server to the fourth server don't depend on each other. They can all get them independently. The problem is that once you fork something, it's in a separate process. There's not a lot of getting data back. So basically, this was my first way of attacking this. So the first thing that you got to do, and for a more in-depth dive, I would recommend the server talk that was given a few years ago. I do believe that is recorded and online, is you need to hook into the child signal. This will be every time one of the children are done, they will send something to this signal. If you ignore it, you get zombie children. It's just a whole bunch of processes running around. Not good. Not good. Bad time. So basically, you assign it a method. I've always called mine Reaper of Children because it's basically there to find out what happened at the end of the child's life. Very sad. But anyway, so Reaper of Children, basically, it uses the POSIX, the no hang. And this is a safe way of being able to listen for the children with a non-blocking manner. And basically, the only thing you're doing is, as the child is done, you're deleting it out of this hash, and you'll see why in a second. So this is the magic. This is where the magic happens. Again, we have our for loop over all of our nodes. Then we do the fork, and basically, at this point, we get two programs that have copied everything. The parent gets the child process. The child gets 0. Undef means it didn't work, and you should probably have a die. Yeah, in fact, you're unable to fork. So here, the parent does this, then jumps down and continues on, spawns the next child, so forth. Very important. This section is the child. You need to exit at the end of the child. If you don't include this line, it'll run off, and then all of a sudden a child will start spawning more children and more children and more children, and that's just pandemonium. So anyway, in here we basically get the health information that we need. We put it in our little data structure. Now how do we get it back? My first genius moment, I'm just going to stick it in a temporary file. So I get a temporary file, I put it in /temp, but you can put it anywhere. I write my data to it, and then that's it. After we've spawned all the children, and all the children are happy running their little programs, we wait, pardon me, we wait for the children. And that's basically, while I have keys in children, remember the Reaper deletes out of children. So when there are no more keys left in here, this is done. It basically just loops over this, and if you have verbose turned on, it'll print out this nice little message letting you know what it's waiting on. Once it's done, you basically open up your final, you open up your file and build page goes in, gets all of the temp files, and then builds the page. And it's basically, this is a little bit more eloquent than my first attempt. Actually, literally in my first attempt, I wrote an HTML snippet here instead of stuffing a JSON representation of the data, which then you could do anything with later. And then what I would do is I would take all the snippets of HTML snippets and glue them together into one big HTML file. Yes, sir.
Why the sleep 2?
Just,
Like that could
it could be sleep 1. I could be sleep 5.
whole thing down if you have 100 processes.
Well, yeah, yes and no, but I do have print and execution time. You'll find that this is to slow this down. It really won't slow down your reaping of your children. I guess if you really want to be as time conscious as possible, you could turn this to 1. But then you're just going to, if you have verbose on, then you get a lot of. So yeah, I mean, if you were, I picked 2 at random. It really depends on what you're doing. If you're doing something that's going to come back really, really fast, yeah, you'll want this as low as possible. But these health checks take up to 10 seconds to come back, so waiting 2 seconds, kind of a happy medium. The question was, why sleep 2? So basically, this is what it looks like when we. There we go. Okay. So this is a health check original with verbose mode. As you can see, they're all the children processes that I'm waiting on.
Got it.
And hopefully, okay, now you start seeing it's getting smaller. It's getting, there we go. It's getting smaller, and the whole execution took 10 seconds. I basically dumped everything at it. I put every child to do. And from that, we get this guy, the original. And if you should note, hopefully, of course, I have stopped and started since the last time I generated this page. So that's why these 2 pages look different. From now on, the pages will look the same because I don't want to wait 8 minutes for this. So basically, it's the same report. It should be looking the same, but I messed that up. But it took us 10 seconds instead of 8 minutes. So you run this once every minute. That's great. We have our data. Problems with this method is I'm writing the data to temp files. Fortunately, it's a really quick program. It took 10 seconds to write. The probability of someone clearing up my temp directory in 10 seconds is low. The probability of running out of space on the disk drive, also low, but it could happen. So a lot of things, could happen because you're writing to it. You are listening to your children, but you're doing it kind of they left a note on the refrigerator. It's okay, but if they're saying that, I'm going to go to Johnny's to play video games all night, you might have wanted to tell them no on that one, but this method wouldn't help you with that because you're not listening to them directly. So to help us get around this problem, we get the right program back. We use open. And if you haven't done it recently, I highly recommend reading the Perl Open Tut page or the using Open for IPC in the Perl IPC man page. Open does a lot of stuff, a lot more than I ever thought because I've only ever used it for the one thing. So what Open does, well, it's actually not what's helping us. We're still forking. It's just we're going to use Open to fork now. So what I neglected to tell you the first time around in about fork is fork replicates everything except for file descriptors and sometimes locks on those descriptors. These are shared while everything else is copied. So when you fork something, any open file handles are both accessible to the child and the parent. Now, you really don't want to do this on an actual file because if the child, if you're trying to read from the same file or write to the same file without using the seek command, you're going to run into problems. You're going to have a bad time potentially. But here's a nice way of opening it using a pipe. Using a pipe in this instance, in fact, this is how it goes. This pipe, you can use it for commands as well, but we are only going to use it as in talking to our children. Basically, at this point in time, open will use fork to spawn a new process. And since we're using a pipe with the dash in front of it, what happens is to the parent, we'll receive a file handle that's open. The child will receive no open file handle, but its standard out will be directed into that file handle. So basically, whatever the child prints to standard out will, by the time the buffer is flushed or the file handle is closed, be reported back to the parent. So that gets us to a little bit nicer way of talking to the children. So here you see again, getting a little bit more complicated. We've added child data because now we have to actually get it right away. And again, we have our reaper. And this time, when the reaper sees that a child is exited, it will get the file handle, which we stuff into the children's hash for each process. We'll read from it and then stuff it into our child data. Again, this is basically happening asynchronously. That's why we need to have this defined up above. Again, we have our loop. Here we have our wonderful new way of forking with the open. And again, with the parent, we take the process ID and we stick the file handle into that hash. This is how we keep track of it, or how I'm going to keep track of it. There are many ways you can go about this. Then again, here's your child. There's the exit. All it does is it gets the data, it creates its thing, and then it prints it. It prints it to standard out. That's all it needs to do. Now, the minute that this prints, it's not like it prints and then magically it appears at the parent. We'll talk about that in a little bit. I won't answer that. It's when the file handle closes, that's when, or when the child ends, that's when basically the print the print will be fulfilled, if you want to call it that. So once it prints it out, it exits, and again we wait for the children. And while we're waiting for the children, as they pass, we reap their information. And then now, instead of having to wait for data to pull it out of files, we simply pass our all the children's data, all their hard work into our build page, and boom, it's done. And you're going to notice that this thing is going to look and feel exactly like the first one. I call it health check pipes. And so just again, the last one was 10 seconds, and this one should roughly be the same. It really depends, since it's a random, how long it takes. Maybe we can get lucky. Maybe all of them will be shorter. But for some reason, there always seems to be one long one. Oh, and it's done, but it still took 10 seconds. This time, to try to differentiate the pages, you'll see that in front of the quote-unquote name, it says original. So here it should say pipe. Let's refresh that. So as you can see, that was done at 7:26, which is now. And now I can show you that outside of, instead of saying pipe and original, they are they show the exact same states. So really not much different, but the thing that you learn here is how to listen to a child. Now, the unfortunate drawbacks of this method are that it's one-way communication, sort of. Basically, as the parent, you can pass data to the child because, the child has everything that you have, but it's kind of a one-time thing. And then you can only listen back at the end or, when you're flushing the buffer. So it's basically kind of a one-shot. You wait until they're completely done, then you get it back. This is not for long-running processes. There are other methods for reading from long-running processes, but actually this is not, the fork is not a good use for it. Threads would actually be a better way of doing it, but Perl does offer some way of doing it using the select statement and using the vector, turning an array into a vector where the select looks across the array and something else, and I could not understand what it was. So basically, this is great for short-running processes. This is not a good way if you have, let's say, a child that's going to run for 5 hours, and in the middle of it, you'd like to get information on what their progress is. Of course, if it's going to run for 5 hours, eventually that file buffer will, clear out, and you'll get some information, but it's not going to be reliable. So again, you want to keep this for short processes. Again, why this is a good idea for like a health check program. Checking the health of a machine usually is really quick. You have a ton of machines to do it, and hopefully your entire program should be done within under a minute at which time you can kick it off again and keep going. The last limitation, I've kind of hinted on it before, is fork bombing. If, I have 101 instances, so I'm not going to have this problem. Never run this on bash, by the way. You will reboot your computer if you do. Fork bombing is basically where you generate processes and generate processes and generate processes until your server, your computer, cannot do any more. If you forget to put an exit out of the child, so in other words, the child continues on and then it becomes its own parent, you are basically doomed to reboot your machine. You cannot control C out of that because your system is busy. So the question then becomes, what is a good number of processes to do at one time? And unfortunately, I didn't find a good answer for that because even on my Mac, I could run several instances of these programs without any problem. You can have up to several thousand, tens of thousands of processes all running at the same time. Really, you're just going to fork bomb your system if you're doing something bad. Now, just because that's the reality, it's not, you shouldn't be that one person hogging everything. Just because you can use 30,000 processes, maybe you should leave a few for that other person using the machine, or, if you want to receive email on your machine. So this is kind of the last step in the concurrency part, is you need to be able to say, no, that's enough. So here I got sick and tired of writing over the same old code, and I kind of stuffed it into a module I call Jundy Concurrency. And basically, I'm just including it right here. And there are, if you download the repo, there are instructions on how to get this all running locally. It'll actually go pretty easily. But basically, when you kick it off, you say, this is the max number of children that I want to run. And then, I guess I can do it this way. Whoops. Then
is there a default value for that? Or?
It's 0. It lets you run all of them. The default, and I'll show you that in a second. But this is really nice. So then you have this is what your child does right here. You basically take that method and you register it with the Jundy Concurrency module. And of course, you pass it any arguments that it needs. And then you'd say to wait. And once it's done waiting, you can get your data from the module using getData. So that makes it look so nice and compact and nothing to worry about. Well, it's because I've hidden all the ugliness, not in that file, but in this one. So yeah, here's where this is going to be. It's basically a singleton from the Java folks. I will only create one instance. No matter how many times you call new, it will only come up with that one instance. If you're doing concurrent things, you just want to be careful. So you probably wouldn't want to do 2 concurrent things right on top of each other. Well, maybe you do. Maybe I need to think this through a little bit more. But in this case, I'm only doing one at a time. So this is where you get the defaults in, is when you're creating it, the max children is set to 0 unless you send in max children. And then I have some other things that I need that you can't override. Have some, making sure that everything is good. And then you get your instance on calling new. But basically, when you register your subroutine, this is what it does. If it counts the number of children you've created. So if you have max children set, and the number of children you have is greater than that, then basically it pushes it onto this hash called, or onto this queue called future children. These are children that I will have in the future. Insert your dirty jokes there. Then it does the exact same thing. It opens up, for if you can run the child, it opens up the file handle. It does the appropriate die if it didn't get one. And then it basically, puts in the file handle, it increments child count. And for the child, it just executes the subroutine with whatever arguments you passed in. It does the wait, does the exact same thing. And basically the Reaper, it's just a little bit more complicated because I did allow you to specify an unmarshal methodology. I hate the word, but I don't know a better one for right now. It basically means that I want it to be, that the information coming back from the child is in JSON. So here, if we'll note it, nope, not there. If we notice that when we created the Jundy Concur, we told it to unmarshal, you need to pass it through this method, decode JSON, which is from the JSON XS module. So if If it comes back as a string and you can unstringify, you chop it apart later, then that's fine too. But if it's JSON and you need to read it from JSON to turn it into an object, that's basically how you do that there. And if you have unmarshalling defined, it basically takes in the information it got from it, and it will pass it through the method and then stuff it into your child data. If not, it just basically takes the lines that I got and stuffs it into your child data. So literally, you could just kind of keep this out of this and basically say, when I get the child data back, I have to go through every method and decode it. But I just stuck it in there. If this is an error, I haven't figured out a good way of recovering from the error. I just log it. So, and then basically, it decrements your child count. And if you have future children, it goes ahead and registers it, so the whole thing can start over again. And yeah, basically, this is just the whole way of being a good citizen. So, as I said, I hold on. There we go. I set it to 10. Set it to 10 methods. 10 children. There we go. And here we can see its children are still running, and there are 10 of them. And if you notice, the numbers are changing. So children are finishing, and future children are coming into being. And they keep going. And so this is a good way. Is basically, you have the parent-child plus 10. So you have 11 processes going. And that way, if there are other people using the machine, you aren't killing the machine for yourself or other people. And usually, if it's your own server, then it's just yourself that you're hurting. And again, in this kind of instance, 100 instances is not going to kill you. But what if all of a sudden you have to spin up 1,000 more? Do you want to all of a sudden have 1,101 processes running? And it gets down here and it's done. And we see it took 44 seconds to run. So that's basically be a nice citizen primarily to yourself. You don't want to have to reboot your own machine, especially if it was an expensive operation like this one, 10 seconds for a health check. You should really need to talk to that programmer. So just to give some ideas, I ran this script all day today with different numbers. So this is basically the number of processes that I would allow, and this is how long it took. And each of the dots basically represents one instance. As you can see, when I allowed 100 processes, they were right around 100 processes. 100 processes, they were right around 10. It was basically 10 seconds. All the way down to when I ran it for two processes at a time, it was actually at in between 180 and 150 seconds. So even, that's a crazy thing to know. When you run it at one at a time, it's 8 minutes. If you run it just at two at a time, I thought I was looking at 4 minutes, but instead I'm 160 seconds, which is what, 3 minutes? So it's a little bit better than half, which I don't fully understand, but hey, I'll take the win. The other thing you can kind of see, again, this is very unscientific. This is my laptop, but it's good to realize it. So I have 101 services that need to be looked at. So pretty much when I did 100, I'm checking them all at once. But if you notice, if I just did it, there isn't really a huge increase in time, in overall time, until I get to the 40 process mark. So basically, I could easily say, oh, well, just check half of them at a time, and I won't be off that much more. Instead of it taking 10 seconds, it actually will end up taking somewhere around 16 seconds. So it's just fun. It's also to note that going from 2 processes to 5, well, that does seem to kind of have it, but basically at a certain time you get diminishing returns. Obviously, you do end up running into you'll never go faster than 10 seconds because one of those stupid health checks is going to take 10 seconds to return. So basically resources, you have the Git repo, which I didn't put here, unfortunately. If you don't want to try to use my thing or write your own, unfortunately, you search on CPAN for Parallel. That's where all the concurrent libraries are. If you search for concurrent, you won't find anything. Man pages, definitely check out the Perl Open Toot and Perl IPC pages. It's just really cool, especially the open one is really cool reading. Perl Fork and Open, of course, and these are the two places where I kind of read up on parallelism versus concurrency. And this is a great talk by Rob Pike, who wrote Go. And he talks about his feelings on concurrency versus parallelism using gophers. It's kind of fun. Any other questions before I wrap it up?
Are the slides in your GitHub repo?
Yes, they are. Actually, I will have to I have to merge this because I made a few changes. But everything is in the slides, the examples, the README page. Actually, I guess I can just. I mean, I put it all together. I can show off my handiwork. There we go. So yeah, it's Perlmonger, GitHub, skeleton key, Perlmonger's concurrency, and the README file basically has the resource links and then how to run everything. It does require Docker to start up all the instances, and it does come with a script that actually starts them up for you and stops them, so you don't have to do that by hand. So, but all the code, each individual codes are right here, including the program that runs the health check concurrent program to let you know how long each one took. So, anything else?
Well, just a question. I mean, for me, as from a recruiting standpoint, how does Golang and Perl like work together or Python? I mean,
Well, I don't. Yeah.
Are they like really important for us for our Ticketmaster like stack? I mean, how important is that for us?
Well, I mean, Perl is falling out of favor, but I mean, it is the workhorse that up until 2 months from now, as I'm told, it's driving most of the mobile traffic sales that we have. I mean, basically, the code base, it's been a Perl code base, and it's been that way for 19 years, for a long time. Go, I found the transition to Go very easy. The Go philosophy and the Perl philosophy is very much do-it-yourself. Go does have a much nicer bumper rails on it. You're not going to wipe away your entire server like some programmers have done before by accidentally mangling Perl code. Python and Perl very similar. They kind of come out of the same school of thought. As far as what we do here, it's like again, Perl is diminishing. Go is up and coming, and of course Java is the business language. But you would be hard pressed to find a large company where they don't have some big amount of their code base probably written in Perl. Okay. Yeah, but it's also, I mean, obviously I enjoy I enjoy most languages. Let's say there's some that I loathe, but Perl will always be my first love and probably my go-to for real quick script answers. And it works since its integration with the shell. And shell commands and getting to the shell is so easy. It makes doing repetitive tests very, very easy. Like, again, like I said with the health check example, I mean, literally you're just doing a wget on the health check endpoint of X number of servers. If the dashboard that I have sitting up at my desk, every minute there is a Perl script that's hitting 200 to 300 servers. Just to get and to report up and unlike this health check where you see every server, it basically does it by region. And so each region, basically, if the region name is red, that means the region's okay, but some of the nodes may not be. So you can get really creative. You don't always have to look at this. You can get creative with how you display this. And in fact, that's the point of trying to just read through a JSON body from the children, is that you don't have to, like I do because I'm lazy, display this information in the HTML table. You could basically put it into a JSON, construct a large JSON body, hand it to this, and have some reactive JavaScript where you can click at it and show, all kinds of stuff. So, but you'd have to be a better front-end engineer than I am, which looking at this, I think anybody is. So, all right. Well, thank you everybody for coming by. I hope you have a good month and enjoyed the talk. Next time we'll hear about threads.